what we're going to do is we're going to continue discussing about reactions. So like I mentioned, so chapter 6 introduced us to some of the parameters, thermodynamic as well as kinetic, that we need to know as we embark on this journey to discussing reactions, to learn more about reactions that are common in organic chemistry. Now, as we go through these reactions, we're going to encounter some intermediates. Now, this came up in some of those reaction profile diagrams. So what we're going to do today is, or in this video, focus on some of the intermediates that you would encounter in organic reactions. Now, we're going to encounter these at various points of time between now and the end of the semester. We're not going to see all of them in like one chapter, okay? So what are some intermediates in Ochem reactions? Okay, so this is what we will be looking at today. So what are some of the common intermediates that we will see in organic chemistry reactions? Now again, just to draw some parallel to what we had discussed earlier, remember that in chapter 6 we talked about reaction profile diagrams. So we had the reaction coordinate on the x-axis, y-axis was energy, and what we saw is that for most reactions, what happens is you start from your reactants and then you go up in energy, and then through transition states. So that's a transition state. This is another transition state. This is a third transition state. So we are looking at a reaction that goes through 3 steps here. So this is one step, this is second step. So this is step 1, this is step 2, and this is step 3. And there's a lot of information that we can actually gather from this reaction profile diagram. So we can tell that this is a 3-step reaction. We can also tell that based on the energies of these, we can say that the first step is endothermic, because the energy of the product from the first step is higher than the energy of the reactant. Similarly, the second step is exothermic, because the energy of the product, which is now here, is lower in energy than the reactant for the second step. Okay, and then the third step is also exothermic, because overall the product is lower in energy than the reactant for the third step. So we did it step by step. You look at reactants and products from every step. And also remember that the valleys here, okay, in some sense, the energy minima, these are the intermediate. So this is I1 and this is I2. So that's the first intermediate, this is the second intermediate. So please refer back to the energy profile discussion from chapter 6 to look at some of this. So essentially what we're doing right now in this video is to talk about these intermediates. What are possibilities for intermediates? What sort of intermediates are we going to encounter in organic reactions? Okay, so there are basically 3 kinds of intermediates. Okay, so there are more. Okay, so 3 carbon-based intermediates that we will encounter. So you're basically referring to the carbon-based intermediates. Okay, so the first kind of intermediate is a carbocation. And then we have radical, and then we have a carb anion. So these are the three intermediates that are most common in the reactions that we will be seeing. So we have a carbocation, there's a radical, and we can make it specific and say that this is a carbon radical, and there's a carbanion. So as you can imagine from the name, it says carbocation, so there's a carbon with a positive charge to it. So I can draw this out as this. So this is a carbon which has a positive charge to it. A carbon radical, okay, a radical refers to a single electron. Okay, it refers to a single electron. So over here, we are referring to a carbon which has one electron on it. So it's not a positive charge, but it's one electron. And a carbanion is a carbon which has two electrons or a negative charge to it. Now I've drawn these species in their respective geometries to show the respective geometries. And again, since we know how to calculate or how to predict the shape, what would be the structure around an atom, we've done that earlier because that's derived from the hybridization. So essentially we can predict the hybridization of these carbons, and that would tell us what the shape should be, the geometry around that atom should be. So for this particular carbon, this here, okay, what would be the hybridization on this carbon? How do we do that? We're going to count the number of groups around this carbon. And remember, this includes the number of bonded electrons or maybe lone pairs, things like that. Bonded atoms or lone pairs, that's it, okay? So this carbon has 1, 2, 3 bonds to it, sigma bonds to it. So single bonds, that's what we count. We don't count the pi bond. Okay, so 3 single bonds to it. There's no lone pair or anything on it. So that means this carbon is sp2 hybridized. That means a carbon that's carbocationic in nature is sp2 hybridized. And sp2 hybridized means that this structure should be trigonal planar. So essentially I've drawn it in a trigonal planar geometry. Okay, that's what I'm representing here. When we go to the carbon radical, this again has 1, 2, 3 groups or 3 sigma bonds to it. So that will be 3 groups around it. Now there's a single electron, but that does not count. It's a lone pair. A pair of electrons would count as a group, but not a single electron. So this carbon is also sp2 hybridized, which means this is also trigonal planar. Okay, and then finally the carbanion. This is now, maybe I should mention this. What I'm trying to say here is there is some group here. So treat all of these as bonds that are connected to some groups. Okay, so a carbanion has 1, 2, 3 sigma bonds to it, and it has a negative charge, which is basically 2 electrons or a lone pair in some sense. It's not a lone pair, it's a pair of electrons, which gives it a negative charge. Okay, and so there are 4 groups around it, which means a carbanion should be sp3 hybridized. And so this carbon now should be tetrahedral. So that's why I've drawn these down, pointing down with the electron pair on it. Tetrahedral, or it will be almost like a nitrogen that's sp3 hybridized. So it's probably pyramidal in shape if we say that we cannot really, if we ignore those lone pairs when we are actually talking about the geometry or the shape. So it's going to be tetrahedral. So these are the 3 intermediates that we will be encountering as we go through organic chemistry reactions. Now, I want to discuss these in a little bit more detail, especially their stabilities, okay? Because that's a very important feature that we need to talk about. And we will start with the carbocation, and then we can basically extrapolate that or use that information to the carbon radical and the carbanion. So we'll start with the carbocation, and we'll see what sort of features would determine the stability of carbocations. Okay, so we have a carbocation. This is a carbon with a positive charge to it. Now, let's consider a few different carbocations, okay? So we're going to consider a few different carbocations. So let's assume we have a carbon with three hydrogens to it, and this carbon has a positive charge to it. And then we have a carbon with a methyl group to it. And this carbon is carbocationic in nature. That's the positive charge. Now, going back to geometry, shape, or the orbital discussions, the molecular orbital picture of these, not the molecular orbital picture, but the orbital picture of these, not the orbital picture of these of an atom that's sp2 hybridized. Realize that when an atom is sp2 hybridized, okay, this is again going back to chapter 1. When an atom is sp2 hybridized, this has three groups around it, and it has a p orbital on it. Sorry, let me grab a blue marker. Okay, so it has a p orbital on it. So let's say that's a p orbital. Okay, so the carbon is sp2 hybridized, so it should have an empty p orbital on it. That p orbital does not have any electrons. Please refer back to chapter 1 if you want to read about this a little bit more, or just refresh your memories on that. Okay, so similarly here we have carbons that are sp2 hybridized, so that means these carbons also have these p orbitals on them, empty p orbitals, because it's a positive charge, so there are no electrons on that carbon. Okay, now let's say if we had these two carbocations, and we'll try to define them, call them a name, you know, based on what we're seeing here. So let's see if it's appropriate. If I look at this carbon here, this has three hydrogens attached to it. So if it's appropriate to call it a methyl carbocation. Okay, so this is a methyl carbocation, a carbon with three hydrogens, because it's a methyl group, or it is derived from a methyl group, a carbocation derived from a methyl group. Now, similarly, this one here, we can call it an ethyl carbocation. Okay, that's an ethyl carbocation. Or if I wanted to generalize it a little bit, if I wanted to be more general, I think I can call it a primary carbocation. Now, we already went through the discussions of what primary carbons are, secondary carbons are, tertiary carbons are, things like that. So when you look at that carbocationic carbon, or the carbon that is positively charged, what we notice is that it's connected to one other carbon containing group. So this is a primary carbon. So it's a carbocation that's derived from a primary carbon. So that's why we're calling it a primary carbocation. So now the important question that we need to ask here is, what's their stability like? Is one of them more stable than the other? Okay. Which one is more stable? So what are some parameters that we have that would help us understand the stability here? Now, in a very crude sense, we can talk about inductive effects, okay? By which, remember, we talked about inductive effects in the acid-base chapter. When you have electron withdrawing groups on an atom, they're going to withdraw electron density from that atom. So that's like a negative inductive effect. It's basically taking away electron density. Similarly, when you have carbon containing groups, these can push electron density towards an atom, or any alkyl group in sense. Okay, alkyl groups, they would push electron density, so that would be a plus I effect. Okay, they would donate electron density, and in this particular instance, this carbon, which is cationic in nature, this is lacking electron density. Its octet is not complete, so it's not feeling stable. Okay, it wants the octet. No, it will not get an octet of electrons, but when the methyl group pushes in some electron density, that will make this carbocation more stable, or at least feel a little bit more stable. Okay, so that's a very crude explanation of why this primary carbocation may be more stable than a methyl carbocation. But a better explanation for this is from molecular orbital picture again, where essentially what happens is we have this empty p orbital, which does not have any electron density, but next to it, there is this sigma bond between carbon and hydrogen. So this bond has electron density in it. Okay, this has electron density in it, and that's the anti-bonding part of the sigma star part of the orbital. Yeah, the sigma star orbital. We don't have to worry about that, but there is electron density in this bond. This bond has 2 electrons in it. Okay, and so what can happen is, because of proximity, since this sigma bond, which contains electrons, okay, so this is empty, whereas this is filled. This has electron density in it. And so what happens is, because of the proximity, this sigma bond can basically share some of its electron density with this empty p orbital, okay, because of this empty p orbital. And that would make this carbocation feel stabilized, because it is now getting some share of the electron density from that p orbital. Okay, so that effect is called hyperconjugation. Hyperconjugation, that's this effect. The sharing of electron density from a filled sigma bond with an empty p orbital in this particular sense. That would be called a hyperconjugation effect. And so the hyperconjugation is going to make this carbocation, the primary carbocation, feel stable. Now, this hyperconjugation effect is not possible in a methyl carbocation because there's no sigma bond over here in space. Okay, there's no sigma bond here or here, because those are the sigma bonds that can actually align. So there's a geometric requirement for this. So the sigma bond must align with this empty p orbital, and that is just not possible in a methyl case. So a methyl cannot do that. And so a primary carbocation is going to be more stable than a second than a methyl carbocation. Now we can extrapolate this. Okay, we can include other sorts of carbocations. So let's say if I were to erase this, well, I think I'm kind of lacking space here, but let me just erase all of this and draw it again. So now if you were to like basically expand this beyond just methyl and primary, and if you were to look at methyl carbocation, and I'm using a methyl group as an R group, but it can be any alkyl group. Please remember that. Okay, this is an alkyl group. That is all I'm using this methyl group to represent here. So thus we have a methyl carbocation, we have a primary carbocation, and then we can imagine a carbon with two carbon containing groups. So now we are looking at a secondary carbocation, because you can notice how the carbon with the carbocationic nature has two carbon containing groups connected to it. And you can imagine a carbon that's tertiary in nature. So it has three carbon containing groups, each with some groups on it. Okay, and I'm kind of, I haven't drawn out the methyl groups, but it should be very similar to the secondary. So these methyl groups can all be drawn out. And essentially what this means is in a methyl carbocation, you don't have any possibilities for hyperconjugation. A primary carbocation has an alkyl group on one side, or in principle, you have 1, 2, 3 sigma bonds that can all contribute to that MTP orbital, okay? Because these all have that MTP orbital on them. Okay, so they all have that MTP orbital. And in case of a primary carbocation, you have 1, 2, 3 sigma bonds that are potentially available for this hyperconjugation effect. When you go to a secondary carbocation, you have 3 and 3, 6 sigma bonds that are available for conjugation, hyperconjugation. And then in case of a tertiary carbocation, we have 9 sigma bonds that are available for hyperconjugation. So the more hyperconjugation you have, okay, so more hyperconjugation means more higher stability, okay? So more hyperconjugation would mean higher stability. So that means in case of carbocations, what we can say is that a methyl carbocation is the least stable. So it is less stable than a primary carbocation, which is less stable than a secondary carbocation. And then the tertiary carbocation, this is the most stable. So this is the least stable, and this is the most stable carbocation among carbocations. Okay, so whenever you're, in fact, happens is like the tertiary carbocation is like way more stable than like a secondary, which is again like more stable than a primary. So there are some exceptions where, you know, primary carbocations would exist, but usually we don't talk about species like a methyl carbocation. They are rarely invoked in reactions. Okay, so we mostly talk about like tertiary or secondary carbocations. So that is as far as carbocations are concerned. Now we can take this same knowledge and apply this to radicals now, the second class of intermediates. So when you have a radical, I think we're going to see something very similar. So when you have a radical, you can imagine a carbon with 3 bonds to it. Okay, and this has 1 electron, and then we can compare this to a carbon with 1 alkyl group connected to it. Okay, so this is a methyl radical. This is a primary carbon radical. And then we can talk about I think we've seen this for carbocations already, so I don't have to draw these out. The structures would look similar. Okay, we can talk about a secondary carbon radical, and we can talk about a tertiary carbon radical. And since these are all sp2 hybridized, something that we already worked on already, okay, these also have an empty p orbital on those carbon atoms. Okay, so the carbon with the radical to it should have an empty p orbital. Okay, so those are our secondary carbon radical and tertiary carbon radical. Okay, now as you can imagine, or as you can probably think, these carbons, the radical carbons, they're also lacking electron density. They don't have their complete octet, which means additional electron density is going to make them feel stable. And so very similar to what we saw in the case of a carbocation, what can happen is the sigma bond here between the carbons and the hydrogens, this can be shared with that empty p orbital, and this can result in hyperconjugation. So the hyperconjugation effect would also work for radicals. Okay, that's the hyperconjugation that we're talking about. And so essentially what would happen is, because of the hyperconjugation, a primary radical, a carbon radical, should feel more stable than a methyl radical. Similarly, a secondary carbon radical should be more stable than a primary, and then tertiary should be the most stable because it has the most number of sigma bonds that are available for hyperconjugation. So the order of stability is again similar to or it parallels the order of stability for carbocations. Tertiary carbon radicals being the most stable, then the secondary carbon radicals, primary carbon radicals, and methyl radicals. Okay, so that would be the order of stability for radicals, and this again is based on hyperconjugation effect. Okay, now the last of the intermediates is the carbanion. Okay, that's the carbanion, and for a carbanion, now we are talking about a carbon which has a negative charge to it. So it already has electron density on it. And to keep it simple, we can compare a tertiary versus the methyl, and then basically expand it to include the secondary and secondary and primary. Okay, so now this is a tertiary carbon radical, sorry, carbanion, not radical. This is a tertiary carbanion. This is a methyl carbanion. Now, the carbon here, this has a complete octet. Okay, so both of these, they have complete octets, which means they don't want to see a lot of electron density around them because that will cause repulsions, or the hyperconjugation effect is not going to help a carbanion feel more stable. In fact, that kind of a sharing would cause repulsion because there's electron density in the carbon and there's electron density in these groups actually. And so for that reason, what happens is a methyl carbanion where there is no sigma bond that can be shared with that pi orbital, this should be the most stable. Okay, this should be the most stable, and this would be the least stable. And so overall, the order of stability, okay, the stability order for carbanions is methyl carbanion is more stable than something like an RCH2, which is a primary carbanion. This is more stable than an this is more stable than a secondary carbanion, which in turn is more stable than an RCR with a negative charge. Okay, so this is methyl, this is the most stable, this is primary, this is secondary, and tertiary. So this is opposite to what we saw in the case of carbocations and carbanions. So more groups make it less stable. So methyl is the most stable, and the tertiary carbanion is the least stable among these. So, and again, now, since we're talking about stability here, you can always relate it to reaction, like is it going to react or not? So if a tertiary carbanion is less stable, that would mean that it would like to react. So it should be like the most reactive among these, okay? So that would be like the most reactive of the carbanions, a tertiary carbanion. Okay, so that's the discussion on like the different kind of intermediates. Again, we've focused on carbon-based intermediates. Now we'll see other sort of intermediates, but we'll basically expand our knowledge of these carbon-based intermediates to those intermediates and use similar discussions to talk about them. Okay, so that's a discussion on the kind of intermediates that we will be encountering as we go through the chapters. and we're going to start with reactions in the next video. Thank you for watching.